Welcome to the Explainer. Today, we're going to dive deep into one of the most fundamental and surprisingly tricky tools in all of data science, generating random numbers with NumPy. Now, I know it sounds simple, but getting this right is absolutely key to building models you can actually trust. So here's what we're going to cover. First, we'll pull back the curtain on what randomness even means on a computer. Then, we'll explore NumPy's awesome toolkit for this and zoom in on that famous bell curve. After that, we'll tackle the super important topic of reproducibility, and we'll finish up by looking at the beautiful mathematical reason the bell curve shows up pretty much everywhere. Okay, let's jump right in with a question that, honestly, trips up a lot of people when they're starting out. Think about it. How can a computer, a machine built on pure deterministic logic, ones and zeros, ever create something that's genuinely unpredictable? So are they really random? The short answer? Nope, not at all. A computer is predictable by its very nature. You give it an input, it follows a set of rules, and it gives you a specific output. Every time. So what we're dealing with isn't true random. It's actually something way more interesting. And, for what we do, way more useful. And this right here is the magic trick. It's called a pseudo-random number generator, or PRNG for short. Just think of it like a super complex mathematical recipe. You give it a starting ingredient, that's called the seed, and the recipe uses that seed to bake up a number that looks random. Then it uses that number as the new ingredient to bake the next one, and so on. The whole sequence looks random, but it was all determined by that very first seed. And this slide really gets to the heart of the difference. True randomness, the kind you might get from tracking radioactive decay, is totally unpredictable. It's great for things like serious cryptography. But for us, pseudo-randomness is the real hero. Why? Because it's reproducible. And that's not a bug, it's a feature. It's what allows us to debug our code, to have other scientists verify our experiments, and to train a machine learning model twice and get the same result. It's all about that seed. Okay, so let's see how this all plays out in the real world, using the tool pretty much every Python data scientist relies on, NumPy's super fast random module. This thing is built for performance, especially when you're working with huge arrays of data, which makes it a must-have. Now, when we generate random numbers, they usually come in two main flavors. First, you've got the uniform distribution. This is like rolling a single, fair die. Your chances of getting a 1 are the exact same as getting a 6. Every outcome is equally likely. Then you have the normal distribution, which you probably know as the bell curve. This is totally different. Here, things are clustered around an average. Think about people's heights. Most of us are somewhere in the middle, and it's much, much rarer to be extremely tall or extremely short. All right, so for the next little bit, we're really going to zoom in on that normal distribution. And there's a good reason for this. This shape, the bell curve, shows up almost everywhere. I mean, from test scores to blood pressure to errors in a measurement, it's just fundamental to how the world works. You know that classic symmetrical bell shape, right? That's what we're talking about. And that shape tells a really powerful story. The highest point, the peak of the bell, is the most likely outcome, the average. As you move away from that center in either direction, the curve goes down, which means those outcomes are less and less likely. And the amazing thing is, this entire elegant curve is described by just two numbers. It all boils down to just the mean and the standard deviation. The mean, well, that's easy. It's just the center, the peak of the curve. The standard deviation tells you about the spread. A small standard deviation gives you a tall, skinny curve, meaning all your data is bunched up close to the average. A large one gives you a short, wide curve, meaning the data is really spread out. And here's a super useful rule of thumb. In any normal distribution, about 68% of everything will be within one standard deviation of that mean. Let's make this real. Imagine you've got this machine, and its whole job is to fill bags of wheat. But it's not perfect. We measure thousands of bags and find out the average weight, our mean, is 1,023 grams. And the standard deviation is 19 grams. So what does that tell us? It tells us most bags are going to weigh somewhere between 1,004 and 1,042 grams. And check this out. This is what happens when we fire up NumPy and tell it to run a simulation. We say, hey, give me 5,000 samples from a normal distribution with a mean of 1,023 and a standard deviation of 19. And when we plot the results, boom, a perfect bell curve. You can see that big peak right around our average, and it tails off on both sides, exactly like the real world. This is how we model reality with code. So this is awesome, right? We can model the real world, but it brings up a huge critical issue, reproducibility. If my amazing new machine learning model's performance depends on some random numbers, how can anyone else ever check my work? How can I even check it again tomorrow? And the answer to that problem, our secret weapon, is the seed. Remember how the whole sequence of pseudo-random numbers starts from that one initial value? Well, if we manually set that seed to a specific number, say the number 42, we are guaranteeing that every single time our code runs, it will generate the exact same sequence of random numbers. This is an absolute must for any serious scientific work, and trust me, it will save you hours when you're trying to debug something. Okay, but how you set the seed is super important. For a long time, people used nprandom.seed. The problem is, this method messes with NumPy's global state. It's kind of like having one single dice cup for your entire program. If different parts of your code are trying to use it at the same time, they can interfere with each other. It's not safe. That's why the modern, much better way is to create your own little isolated generator with np.random.default_rnd. Let's walk through this. Step 1, we create our generator and give it a seed, say 42. In step 2, we ask for 3 numbers and get a sequence. Then, in step 3, we ask the same generator for more numbers and we get the next 3 numbers in the sequence. But, and here's the magic part, in step 4, we create a brand new generator, but we give it that exact same seed, 42. And look at step 5. When we ask it for 3 numbers, we get the exact same sequence we got back in step 2. That is a game changer for reliable research. And hey, don't just take my word for it. This is straight from the official NumPy documentation. They're telling you, flat out, np.random.seed is the old way of doing things. For any new code you write, default RNG is the way to go. It's just safer and better. So, okay, we've got a really good handle on this now. We know what pseudo-randomness is, we know how to generate different kinds of it, and we know how to control it to make our work reproducible. But there's still this big nagging question. Why the bell curve? Why is it everywhere? Well, the answer is one of the most elegant and beautiful ideas in all of statistics. It's called the central limit theorem, and I know that sounds super academic and maybe a little scary. But the idea behind it is actually incredibly simple and profound. It says that if you take a bunch of random samples of something, it doesn't matter what the original distribution looks like, and you average them together, the distribution of those averages will start to look like a bell curve. And the best way to really get this is to see it in action. So let's go back to our dice. We already know that a single die roll is a uniform distribution, right? A flat line. But what happens if we roll a bunch of dice and start looking at their average? Okay, so here we've simulated rolling just 2 dice and taking their average over and over again. And look at the graph. It's not flat anymore. It's triangular. It peaks right there in the middle, around 3.5. And that makes sense, right? There's only one way to get an average of 1. You have to roll 2 ones, but there are a bunch of ways to get an average in the middle, like a 3 and a 4. Now let's up the ante. What about the average of 10 dice rolls? Whoa. See how that shape is smoothing out? The sharp point of the triangle is gone, and it's starting to get those familiar curved shoulders. It's looking a whole lot more like our bell curve. And for the grand finale, the average of 100 dice rolls. Just look at that. It's a nearly perfect, beautiful, smooth, normal distribution. We started with something totally flat, and just by averaging, we ended up with the bell curve. This is the central limit theorem in action, and it's why the bell curve is everywhere. So many things in nature are just the sum total of lots and lots of little random events all added up. And that leaves us with a really powerful final thought. The central limit theorem shows us that even from simple random noise, an orderly, predictable pattern, the bell curve, can emerge. So it makes you wonder, right? What other complex systems, from the daily swings of the stock market to the tiny errors in a scientific measurement, can we understand better just by remembering that deep down, they might just be the average of many random things?